Welcome to my talk. Good morning. I hope you enjoyed the first day of the conference. Did you? I didn't. I love it. So, I will talk about modules once again, but please don't be scared. It's the last time. First of all, we'll give you a short modules recap. It's not an introduction, it's just to make you more familiar with the terminology. Then we will talk about the compilers and how the status of the implementation of modules in the compilers are. Then I will go through an example of a modularization of an existing library. I will talk about build systems that support modules. I will speak a little bit about module dependencies and why they are so important. And then I will dive into a code demo. This is a continuation of a demo that I gave last year, both here, but also in the keynotes in CPPCon and Meeting C++. And I will expand on the parts that have been missing out or left out of these demo code demonstrations. And in the end, as usual, I try to come to a conclusion. This QR code, this is the instructions where you can get all of the code and also the slides. And as you can see, I'm an electrical engineer by profession. I had my first programming contracts in the final school years in the late 70s. And for some unfortunate reason, I'm still stuck there. I'm also participating in the committee, in particular the evolution working group and also the tooling study group, who is in charge of all these build tool stuff, for example. And I'm employed at a small company in Germany. We build machines. This is kind of industrial embedded, what I'm working on. So let's dive into modules. This is probably the shortest introduction that you will ever get in your life about modules. In the traditional compilation world, we have libraries that have an interface usually implemented as a header, and we have implementation files, and this combination is called by John Lakers, hopefully you know this name, a module, which it isn't, but anyway. And these users of the library just include the interface header, and the meaning of the interface headers and the contents in there depend on at which point in the client translation unit the interface is actually included. So there might be different interpretations of the textual code that you have in there. And this might lead to ODR violations that we all love and hardly ever see. And yes, this is not just a theoretical kind of thing. I've been suffering from that, in particular in preparation of this talk, a lot. So what does the compiler do when it translates such a translation unit from the user? It starts out with no declarations, and it collects them through the whole compilation of the translation unit. It starts out with a couple of macros from the command line or predefined, and the same with compiler options. And at the end of the translation, it writes out, hopefully at least, an object file, and everything else is discarded. And the next translation unit, the same is going on and on and on. What changes with modules is that the interface of this library that I've been alluding to is no longer a header file, but it becomes a translation unit on its own. So this is why the interface of a library is no longer a header, but an interface unit, a translation unit just as any other. And the benefit of that is it doesn't start the compilation and the meaning of the text in there with something that has happened before the textual inclusion, but it starts right out from the beginning of the compilation. So we have full control about which macros there are, what kind of compiler flags we give, and all of that. And it also means the interface of the library is compiled only once. So there's no divergence in the meaning of the text in our code. The problem is translation units in both C and C++ are independently compiled of each other. So how do we transfer the contents of the interface to both the implementation of the library and the users who want to use a module? And there is a new channel that has been invented, and this is called a Build Module Interface, in short, BMI. Everything that the compiler encounters, you've seen one of these columns there, goes into this BMI file, and the BMI file allows that other translation units know what is actually contained in the interface of a library, for example. And the difference is the constituting parts of a module see all of the entities that are stored in a BMI, whereas only selected parts of the contents in the interface become available to the users outside of the module. So you can tightly control what you make available to your users of a library. The compiler does basically the same thing when it compiles such an interface. The biggest difference is it starts out by 0, and in the end, it doesn't throw away all of the declarations in there, but rather it serializes it into the BMI file. And usually, implementations also store a bit of information in there about the initial compilation state, like macros that have been on the command line or compiler flags. This is to make sure that both the user and the producer of an interface are compatible with each other. Compilers can check that, and they actually do. So how does that look like in the real world? A little bit about terminology. In the top, you see the primary interface unit, one of the translation unit types of modules. In the bottom, you see a module implementation unit. You can have as many of them as you like. And then both of these translation units carry a name of the module, and this is the reason why this module type is called named module. And all the parts of code that have this light green backdrop constitute the so-called module purview. This is actually the core part of a module where all the module rules apply. They are slightly different to what we are used to today. Please be aware of the fact that the purview is not a namespace on its own, but it creates something like an independent domain of names that you can have independent from any other module. Then there's the so-called global module. These are the orange parts here. And this is the module that you haven't been even aware that you have been programming in. This is just the same as with the namespaces. C code is in the global namespace, and C++ is in individual namespaces. And with modules, we have the same. We have the named module purviews, and we also have the global module. Each module translation unit can optionally have a leading section where you can have a small fragment of the global module, and this is where you can introduce, for example, the standard library headers or other headers that you already have to make them available to implement your interface or your implementation. And this is introduced by a module declaration without a name. So the global module doesn't have a name on its own. the next thing that we have to talk about, this is exportation of entities through the BMI. Exportedness is not something that applies to the declaration itself. It applies only to names. If you export a name from a module, you make it available to name lookup. And that's the whole secret of modules, if you will. In syntax, as seen before, a module declaration without a name introduces the global module fragment. This is a part of the global module. Then you come to the so-called module declaration, where you name the module or give it a name. All translation units with the same module name are part of the same module. And if you stick an export keyword in front of it, you designate this particular translation unit as the so-called primary module interface. And you can have only one of them, so one file tells the users what to expect as the exported entities from a module. You can import foreign modules into your own module. For example, you want to use entities from there in your own interface. Or you can also make them part of your own module by re-exporting the foreign module. And you still can include header files in here. But please be aware, we are in the module purview. So the contents of this header file become an integral part of the module itself. You can't use the same header within a module and outside of a module. That would designate different entities. And here we see an example of an exported declaration. I say export the name frop of this function declaration here. The other parts of the function declaration are the entities that come with the name, but they're not visible in the sense that we're used to in the traditional work. They are just reachable. So the compiler can use that. You as a user are usually not involved into this kind of thinking. In the bottom, I have a module declaration with the same name, so this is part of the same module, and this designates it as the module implementation unit where I have the function body. Then there's another concept that are new to modules, and this allows us to give modules so-called name isolation. We have a module 1 in the left, a module 2 in the right, and both of them have a non-exported function declaration called foo, as you can see. And these two function declarations do not clash. They have the same name in different modules, so they are different things. Each foo can have a different implementation. And if you import both modules into a translation unit, you can then use the exported functions in there with the function bodies inline in the interface, referring to the individual foo functions, and the linker has no problem using these foo implementations from different modules. This is different from the traditional word. You can't do that in the traditional compilation model. And the secret behind it, there is a notion called attachment. So the foo in the left is attached to the module mod1 in this particular example. So the foo has a different entity foo at module 1 from the one on the right, foo attached to module 2. And this is the same for all names that are part of the module purview. This is the difference that I've been alluding to. All names in the purview of a module are attached to this module. So are not attached to the global module. In the specification of modules, we have a zoo of translation unit types that you can use. I don't go into any details here. We have seen the primary module interface so far and the module implementation unit, but we also have interface partitions, internal partitions, and the so-called private module fragment, and each of them have different properties that you can choose from if you want to build a named module. And we also have something that is completely different from that, in many aspects at least, and these are the so-called header units. This is when you have a header and instruct the compiler to compile it just as a translation unit, and this is where the name comes from. Please be aware, it sounds easy to compile a header. In fact, this is the most complicated type of module translation unit that you can have. And build systems are quite struggling with that kind of translation unit type. The important differences are, in particular, the named modules have a purview with attachment and name isolation, whereas the header units don't. The header units are part of the global modules, whereas the named modules have their own, but they can use parts of the global module entities. Header units can export macros. Sounds great, but gives build systems a really hard time. And named modules have full isolation, so no other stuff can change the meaning of entities, and stuff in modules can change the meaning of others. Whereas with header units, you don't have full isolation. So this is just a short introduction. I've given a couple of talks in the past about the details of that. If you want to know more about it, just watch any of these videos of mine to learn more about composition of modules, the details, and everything. The next section is about the status of compilers and their module implementation. First, we will look at what each of these compilers they self-assess through their documentation or other means of communication. So what does each compiler tell us about the features that they support, how complete the implementation is, what kind of file extension they want to see and take a particular source code as a module translation unit, and which compiler flags you need to give to compile a named module or a header unit. This is a table that you may have seen before in other talks. In talks from the last years, you had way more red marks in there. We are in 2023, and it's quite encouraging to see lots of green marks now. MSVC is actually in a state that would consider it production ready. Clang is very good in the latest incarnation of Clang 17. Even though the modularized standard library is still in an experimental stage and not part of the distribution packages that you can get from the repositories at LLVM. And then there's GCC. An important thing, I've been alluding to it, is the thing called BMI consistency. If you compile an interface with a set of compiler flags and possibly macros, these flags and macros may change the ABI of your interface. And this ABI may be different from the one that you want to import a module into. And to prevent ODR violations because of API differences, compilers actually check if a compiled module interface, the BMI, matches the expectations from the importing translation unit. And MSVC has just a few different flags that you can give, and it looks at them and says, oh, these don't match up, but it's more like a warning that you can ignore and still go ahead. And in some cases, or even in many cases, this just works. Whereas Clang has so many compiler flags that make the perceived ABI of a BMI or a translation unit not to match up. Unfortunately, this list of compiler flags is not documented. It still gives a warning. If they don't match up, you can shut up this warning, but Clang wouldn't accept it anyway. And GCC, I don't know, there's absolutely no documentation about BMI consistency. Let's see what the future will bring. The next part is file names. You may have heard about it. Some people in the community are quite outspoken. They say modules are broken. And what's the reason for that? No implementer agrees to the other implementer what the favorite extension is. It's only about its extensions. So, okay, modules are broken. Let's see what we can do anyways. Each compiler allows for flags that you can give so that they would expect any source file with any name as a translation unit for a module. The same, we have also compiler flags to accept it as a header unit, but we won't talk too much about header units. And as you can see, every compiler has a different opinion what the true extension of a module source file is. Clang loves to have an M suffix there. GCC says it's just C++, okay. And MSBuild says, it's an interface, let's throw an I in there so the interfaces stick out. And that's all about this topic of file names. So at this point, we have learned everything about modules, and we are now fully prepared to build our first module, and we don't start from scratch. We use an existing library, and this library is called ArcPath. It's a C++17 single file header only library. It's totally portable, no dependencies except for the standard library. This is a command line parser. If you know the demo code from last year, I had the command line parser from Boost, but I wasn't too happy about the 25 additional dependencies it brought in. So I thought maybe this year I will change the command line parser, and this is it. It's a very simple library. It's just a namespace. There's a couple of implementation details that are not considered to be part of the interface. And we have just a handful of things that actually form the interface. It shouldn't be too difficult to modularize this, right? Anybody? Okay, I do it. Let's be a young Padawan, keen on modularizing the first library. Just slap a module declaration on top of it and call it aptly ArcPath. Export everything in a group of exports that are meant to be part of the interface. This section of the code here. And that's it, right? Couldn't be easier. If you want to be fancy, just export every entity individually. In some cases, this really helps. But just to give you an impression how this would like, all the exported entities, in particular the forwarded one, have an export. So this is the fancy way. Let's see if compilers accept that. In alphabetical order. First, clang. Oh. Seems like there's something went wrong because it doesn't compile. You don't need to look at the details of the error message here. We know they are long. But it tells something about the algorithm header from the standard library. Okay, just one compiler. Try the next one. GCC in this case, a different set of compiler flags that you can use or must use. Compile it, fail. Doesn't compile. You're probably onto something. Anybody has an idea? Think about it. Also the algorithm header in this case. Our third candidate, MSVC. Another set of compiler flags. Compile it. Oops. It did compile. What's wrong? We got an BMI, we got an object, and we got a warning. It says, include algorithm in the purview of a module appears erroneous. Anybody an idea what was wrong? Nobody? Okay, I will tell you. And it's actually helpful. It says, for example, consider moving that directive before the module declaration. And what's the solution? We need a global module fragment. As I said before, the global module fragment is where the traditional include files live and where you stick them into your module translation unit. And our standard library is part of the global module, so we have to stick all the headers in there, and please all of them. Don't forget any of them. Use any tool that you can get your hands on to figure out if you didn't forget any of them. And don't make the error of including header files from the traditional world into the purview of a module. So let's compile it again, and as we can see, clang compiles now, MSVC compiled before, and GCC, it crashes. It's a segmentation fault. And the problem with GCC is you can look as much as you want at the source code of a source file of a translation unit with GCC. GCC is in kind of a superposition state. You need to actually observe the outcome of the compilation, so such the wave, the Schrödinger wave formula and the field decays into either a crash or a success. Not really helpful in practice, but that's how life is in 2023. I also told you in the beginning, a module interface has actually two phases. One that's looking into the module implementation itself, and during the compilation of the module, we exercise this interface, so it's already tested. But the other side of the interface is looking outside into the user code, and you need to test this kind of phase of the interface as well. Don't forget that. This is a highly lacking integration test. Not every entity of the exported interface is appearing here, but it's a start. You see, I import the BMI of the module, have a little bit of code to exercise the interface. So let's compile it with Clang, compile it with MSVC. Unfortunately, GCC is no longer with us anymore. So what's the outcome? Clang, yeah, this is the compiler flags that you have to give to actually consume a module. Don't forget to include the object file from the interface translation unit. And oh dear, yet another failure. Something about missing declarations. Okay, we have another compiler at our hands. Let's do the same with MSVC. Same problem. Missing declarations. Anybody have an idea? The point is, these declarations come from the included headers in the global module fragment. And entities in the global module fragment get a special treatment. The headers in there are not part of the module itself. So the standard tells us what it thinks we don't use from these headers. And this is quite challenging when templates come into place. Are declarations that are not used. The technical term is declaration reachable, and so they get discarded. The benefit of that is our BMIs don't explode because we would otherwise possibly include the whole standard library into the BMI of the module. There's a good reason for that. The point is, if an entity is discarded from the BMI, the entities in there and the names are neither reachable nor visible. And this means instantiations within the user code have to deal with the fact that declarations are missing. In other words, we as programmers have to provide them. If you can, use the modularized standard library so you don't have to figure out which declarations are missing. Because otherwise, you need to figure out in this particular case, in this particular integration test, we need the any header and the string header, and none of them appears in my own source code. How would you as a developer figure out which headers are missing? Opinions? Dices would help. So, this is the sad state if you use only header files. But there's actually more with this piece of code from the ArcPath library. This integration test was carefully chosen by me to not trigger ADL within the library itself. Usually ADL just reduces the compiler throughput that you can experience in the traditional world just as well. But here, it can also cause lookup failures because many entities that are not exported are not available to name lookup, in particular the second phase name lookup. So this can become problematic if you run into ADL with your templates that you export. And on top of that, we have another kind of thing that has to do with translation unit local entities. For example, if you have something in your interface header or module, primary module interface that has internal linkage, you can't refer to it from the outside. This is just how linking works. And if you have, for example, an exported function that is completely inlined within the interface unit, then you have the body in there, and there you might refer to such a translation unit local entity. Then you expose this translation unit local entity that is not reachable from the outside to the user, and the user code will try to link to this translation unit local entity. And this is a real problem if you don't think about it. So please make sure don't expose anything from your interfaces, be it in the traditional world or in the modules world. Don't expose any of these translation unit local entities through your interfaces. In the modules world, it makes your code ill-formed. In the traditional world, the standard explicitly says this is deprecated. Don't do that. If you don't do that, you're safe. Don't use statics in your interfaces. Don't use anonymous namespaces in your interfaces, but use inline. Because inline doesn't mean inline, it means all the entities are just the same. Okay. Now we've seen the smallest library in the demo code. Let's go to the largest one, ASIO. And what I'm using here is what I call the trinity of modules. We have a primary module, a global module fragment with all the dependencies that are not part of the library itself, platform headers, for example, standard library headers and others. We have the exported entities. In this case, this is a header-only library, or can be used as a header-only library, so we throw all of these headers in there, and we have a lot of them. And in the final section, we have the private module fragment, where you place all of the implementations in here. So in fact, this translation unit is a single file module. In fact, it's a Unity build of the full library. And this means this compiles crazily fast. Much faster than you would compile in the traditional world. And this is without any use of modules so far. So much about modularizing existing libraries. Let's talk about build systems. Which build systems support modules today? Any idea? Any candidates? Okay. Let's do it in some random order. The oldest one is Build 2. Some people might have heard about it. A couple of years ago, it has been supporting all major compilers. As far as I know today, it only supports GCC as module. Please be aware. I talk only about modules. Then there is CMake. Finally, since version 3.25, it has an experimental support for modules, but it only supports named modules, no header units. And it requires quite recent compilers, and it requires also a dependency scanner that comes with the compiler or is built into the compiler. You still can do module dependency specification by hand. I did it. I hated it. And if you ever see a piece of code in the interwebs where people do it by hand, look closely, It's pretty easy that it doesn't compose with other modules. So if you want to use CMake, do it by the book. Then there's, of course, MSBuild that comes with Visual Studio. It's a boring build system because it does everything that you expect. No problems at all, and it's around for quite some time now in the frame of Visual Studio 2019 or so. This is what I have in production. Then there is a new contender that's quite famous, as it seems, in Asia, called CMake. And its biggest benefit, as people claim, it has a nicer syntax than CMake. On the other hand, it has an even worse documentation. So I can't tell you much about it. Take what I've written here with a grain of salt. All the rants are Evoke by Peter Bindels. This is also an old build system. As far as I know, it supports only Clang, and the development is at a well-observable pace. And there's a new one from a guy from Pakistan with a completely new approach. It's quite interesting, and we will probably look at it in the study group 15, where we talk about tools. Let's see how this fares in practice. I have no clue. And hardcore people use Make. Sure, you can do that if you want to do everything by yourself with your own build recipes, but you can do it. So let's talk about CMake. I think most of you are using CMake. Anybody not using CMake? Okay, you're a Make guy. Okay, then this is probably the most interesting part of the whole talk to you. As I said, 3.25 is the first one to support modules. I recommend 3.26 or possibly even later. The current one is 3.27. And it requires Clang 16 and MSVC, quite recent. All of them support module dependency scanning, and all of them can create a so-called module dependency report in a standardized format. And this is the key to the support for modules by CMake. What you have to do, you need to opt into this experimental support by giving a UUID. And in CMake fashion, this UUID changes with every version of CMake. And if you do that, you can use file sets in your target sources directive within the CMake list.txt file, where you can give in the old-fashioned way, the source files for your executable or library. And these are the entities or these source files that consume BMIs. Then you have a file set where you specify the module translation unit sources that create BMI files and are parts of named modules. These are partitions and interfaces. And in the last section, you can also list all your header units that you want to use. They also create BMIs. The only sad thing is that header units are not supported yet in CMake. So in 3.26, the last line is just ignored. And in 3.27, CMake says this is a syntax error. So it's your choice of poison. So the support for modules in CMake revolves around dependency discovery. And you have to opt into that as well. You see 2 more lines here, and these 3 lines need to be present in every CMake text file that you use. Even if you don't want to use dependency scanning, they have to be there, and if you don't get any kind of module support. So it's just a cut and paste thing. So what do you think about all of that I've seen so far? Feel scared? I hope not. This is CMake after all. And I hope this guy is still busy with the people he had scared 100 years ago in the movie theaters all around the world. Nosferatu shouldn't scare us anymore. So let's go into the dependencies, and for example, let's look at the SDL library. SDL is a C library. We can make a module interface out of it. It's a little bit more involved. We have the primary interface, and we also have 2 interface partitions. It has to do with SDL is really macro heavy in its interface, so to get rid of all the macros that you can't export from named modules by using more macros. And yeah, this is why the interface exports, imports the partitions, and you can see the highlighting. The one on the left is using the one on the right, and the one on the right is using the actual C headers. And SDL library comes with a CMake text file. What do we have to do to build these additional 3 translation units for the module? Well, except for the 3 magic lines, you add a file set with the module translation units of the interface. You can glob it if you have a distinctive file extension there. And what does the module dependency scanner of Clang tell us? In particular here, this example is about the module interface fragment at the bottom left. It says the name of this fragment is SDL global macros. It provides this particular interface partition. It is an interface. And by the way, this is the source code of it. And it also requires another module fragment. This is the syntax as it comes out of the Clang dependency scanner. MSVC has it built into the compiler, but in effect, it's exactly the same. Just the ordering is a little bit different, but we don't care about ordering here. So both compilers support the correct format for the consumption by CMake. What CMake does, it creates something that they call module maps. This is something, nothing complicated, it just tells, okay, Clang, use this compiler flag. This is where you have to put the BMI file, and this is where you find the BMI file of your dependency. And the same with MSVC, just the same. And this is all the magic that's required to make CMake happy and support modules. Let's figure out if it actually works in practice. As I said in the beginning, I have a demo code. This is the same demo code, for the most part, from last year. Last year, I've been using MSBuild and the Microsoft compiler only, with a library, a standard library that I have to build myself. This year, I don't do any of these strange kind of things. This is the code where we left last year. I use a modularized standard library. I use ASIO as a module, seen before. In the demo code itself, I have 7 imports from modules from the demo code, and I'm using it throughout the main function of the demo code. And this is the only non-modularized source code in the whole demo. So the module structure of the whole demo is 8 named modules within the project here. 1 header file. Last year it's been a header unit, but you know why? It's demoted again to an include. Out of project, I use these dependencies here for named modules, Azure, ArcParse, libav, and SDL. All of them are named modules, as you can see. And I use the modularized standard library, and I don't build a particular library just by myself and do some changes in there. In this case, I take any standard library as it comes with the distribution, be it libc.c++, be it libc++, or MSSTL. And the build recipe in the demo code can make a modularized standard library out of all of them. So it's demo code time. Let's see if I did lie to you or if it actually works. So first, let's load Linux. I'm using Ubuntu here, and I have the apt packages from LLVM 17 here. And first of all, I will try to configure you see it's Clang 17. And in parallel to that, this takes a little bit of time. I have a pre-configured project for MSVC. Just let's build it. Nothing to do. Okay, let's clean it first. What you see here is the switching between dependency determination and the actual building of all the libraries, modules, and everything. The demo code is compiled, so it actually did work. And therefore, yeah, okay, we have a configured project for Clang 17 on Linux. Let's build it also. Okay, it has built. Does it run? The next question. Yes. If you have seen the demo code from last year, it's just the same now on Linux. It decodes GIF files, sends them over the network, and displays it on a GUI that's built from the SDL library. So, as you can see, we actually can use modules not only on MSVC and Windows, we can use it with CMake in a platform-independent manner, also on other environments like Linux, the MSys environment, and I think this is a quite good improvement over last year. Let's go back to the slides. So what's my conclusion from all that I have been showing you? If there is one thing I would recommend, even if you don't want to use modules on your own, please consider using the standard library as a modularized standard library. The reason for that, you can see it here. I have a file called allstud.hpp here that contains the full standard library that you can include in a traditional way, or you can import it as a header unit, that's the second line, or you can import as a modularized standard library. And if you just include it, do nothing else, only including. On my system that I have been taking the measurements on, this took a bit over 2 seconds to compile. The header unit import took 15 milliseconds, and the import of a named module was not measurable. I think this is a good reason to use a modularized standard library. I didn't differentiate between the include import of a header unit and the import of the named module in the code on the above. If this works here, and it is supposed to work according to the standard, then you can deem your implementation kind of production ready. Not all implementations can do that today. And this fits well into what I've been presenting 2 years ago with the formatting library. It's just the same orders of magnitude where the includes and the imports differ. So this is another proof. Named modules are the future for many reasons. And this is where all the build speed up comes from. It's not the compilation or instantiation of templates. This is just the same as it was before. It's the interfaces that become available through the imports of modules. In the worst case, it's as fast as precompiled headers, even though precompiled headers have a ton of limitations that modules don't have. Modules compose, precompiled headers don't. So taking all of this into account, the complicated CMake syntax, the status of compiler implementations or so, in my opinion, we should say yes to modules. At least this year you can. If you want to dive into modules using Linux, for example, many people do. Clang 17, available since Tuesday. You can do the same on your machine. Once again, if you want to pull down all of this demo code with everything that I've been showing to you, here's the QR code once again. You can look at the GitHub repositories also individually. Here you find also where to contact me. And with that, I happily answer any questions that you might have.